You ever just look up at a jumbo jet, this colossal 400-ton machine, and wonder, how in the world does that thing stay up there? I mean, it seems like it's breaking all the rules, but really it's just following the rules of physics. So today, let's crack the code of the sky. Here's the trick. You have to stop thinking of the air around us as just empty space. To really get how flight works, you've got to see the sky for what it truly is, a giant, invisible ocean. And just like any ocean, it's a fluid with its own rules and properties that, if you're smart, you can use to your advantage. All right, so let's dive right in, shall we? To figure out this whole mystery of flight, we first have to get to know the ocean we're trying to fly through. And the biggest, most important idea to wrap your head around is this. Air is a fluid. Yeah, I know, it seems like nothing. But from a physics point of view, it behaves just like water. It flows, it has substance, and you can push against it. This one idea, it's the foundation for everything else we're about to talk about. Okay, so if we're moving through this fluid, what is it about the air that lets us create that incredible upward push we call lift? Let's break down the secret ingredients. First up on our list is density. And put simply, density is just how much stuff, how many air molecules are crammed into any given space. It's the mass of the air divided by its volume. And to put a real number on that, at sea level, if you took a cubic meter of air, that's about the space inside a big moving box, it would actually weigh around 1.225 kilograms. So see, it's not nothing. There's real substance there to work with. And this is exactly why it's so critical for flight. The denser the air, the more molecules there are for the wings to push against and get that reaction force. It's also why it's tougher for a plane to take off from a high-altitude airports, like in Denver or Mexico City. The air up there is just thinner, less dense. So, that density leads us right to our second key ingredient, pressure. This is the constant force that all those little air molecules are exerting on every single thing around us, all the time. Now get this. At sea level, that pressure is a whopping 101,325 pascals. That's like having over 10 tons of weight pressing on every square meter. The only reason we don't get crushed is because that pressure is pushing on us equally from every single direction. And this is the secret sauce, the big reveal. Lift isn't some kind of magic. It is simply and beautifully creating a pressure difference. That's it. You create lower pressure above the wing than below it, and the airplane goes up. So how does a wing pull off this trick? Well, it's all in its clever shape. That curved top forces the air flowing over it to speed up, and a fundamental rule of fluids is that faster-moving fluid creates lower pressure. Meanwhile, the air under the flatter bottom moves slower, keeping the pressure high. So now you've got high pressure below pushing up and low pressure above pulling up, and boom, that net result is lift. Oh, and a quick little pro tip about temperature, it's directly tied to our first ingredient, density. See, cold air is way denser than warm air. That's why on a really crisp, cold day, a plane's engines and wings perform so much better. There's just more stuff in the air for them to work with. Okay, so we've got our amazing upward force. But the air doesn't just give us a free ride, right? It pushes back. It fights us. So let's talk about the force that's always trying to slow a plane down, drag. And the main culprit behind drag has a fancy name, viscosity. But really, the easiest way to think about it is just as air friction. It's the fluid's own internal resistance to flowing smoothly. I love this analogy. Think about moving your hand through water. Pretty easy. Now, try moving it through thick honey. Much harder, right? That resistance you feel, that's viscosity. Now, air has a really, really low viscosity compared to honey, obviously. But it's not zero. And when you're hurtling through the sky at hundreds of miles an hour, that tiny bit of air friction adds up to a massive slowing force. And what's really cool is how this viscosity leads to two totally different kinds of airflow. On one hand, you have smooth, beautiful, orderly laminar flow, which is like a calm river. It creates very little drag. On the other, you have turbulent flow, chaotic, swirling, messy, like whitewater rapids. That creates a ton of drag. A huge part of designing an efficient aircraft is just trying to keep that flow as smooth and laminar as possible. So up to now, we've kind of been treating air like it's a constant, that its properties don't change. But what happens when you go so ridiculously fast that the air itself can't keep up and actually starts to change? And that brings us to our final property, compressibility. Now, unlike water, which you basically can't squeeze, air is a gas, which means you can squeeze it. You can force its molecules closer together and change its density just by putting it under intense pressure. So why is this a big deal? Well, when you start getting close to the speed of sound, the air molecules literally cannot get out of the way of the plane fast enough. So they start to pile up, they compress, creating this incredibly powerful shock wave that radiates away from the aircraft. And that is exactly what a sonic boom is. All right, we've laid out all the puzzle pieces, the 4 key properties of our invisible ocean. So let's bring it all together. Let's look at the flight equation and see how these forces all play together to make flight possible. You can think of this as the pilot's cheat sheet for the sky. Density tells you how much lift you can possibly make. The difference in pressure is how you actually create that lift. Viscosity is that annoying friction, the source of drag you always have to fight. And compressibility, that's the new boss in town once you decide to fly really, really fast. So let's boil it all down one last time. Flight is not magic, it's just this constant, beautiful balancing act. Lift is all a game of density and pressure. Drag is the price you pay for viscosity. And as soon as you push the speed limit, compressibility changes all the rules. And temperature, well, temperature is the quiet one in the background, influencing everything. So yeah, we've cracked the code for flying in our thick, nitrogen and oxygen-filled ocean of air. But it leaves you with a pretty cool final thought, doesn't it? What happens when the whole ocean changes? What new properties and new rules are we going to have to master to fly a drone or even a helicopter in the super thin carbon dioxide atmosphere of Mars? That's a whole new